Hello friends, welcome to my channel Civil Smart. Today we are going to design a cantilever retaining wall. This is the cantilever retaining wall. We all know that we have different parts of the cantilever retaining wall. This is the vertical stem, right? This is the toe portion. This one is the heel portion. Heel portion is always in where is the backfill soil is there, then that portion is called the heel portion, right? And the front portion is called toe portion. This is the vertical stem, right? And we are going to design this cantilever retaining wall through our Excel sheet. You have to put your data in these pink cells only. I'm going to show the different steps we are going to design through this Excel sheet. Firstly, we will find the depth of the foundation below the ground level, how much the foundation will be there, right? Second step, to find the initial sizes. Initial size, like we have to find the base slab thickness, width of the base slab, right? Width of the stem, how much the toe width, heel width, right? Different kinds of initial sizes we are going to find. Next is the forces and the movements acting on the wall. The different elements are there, like this is the stem, this is the toe, this is the base slab. It will all generate the loads on the particular soil, right? So we have to find the loads coming on the soil by different structures, right? So then we have to calculate the overall movement against this heel. What is the total movement, right? So next step is calculate the earth pressure coefficients, like Ka. We all know this is the active earth pressure coefficient, so it will calculate the Ka and Kp. Kp is pressure coefficient. What is Ka? The active earth pressure coefficient is like when this wall is going away from the backfill soil, right? And when the wall is going in this direction, that is towards the backfill soil, this is called the passive earth pressure. Okay. Next is we have to check against three types of checks are there. We have to check it against the overturning, that it should not overturn, against the toe in an inward or outward direction, both. Calculate the soil pressure below the footing, that the soil pressure exerts from the overall load from the above. It should be less than the bearing capacity of the soil. It is to be checked, right? Next check is the stability against the sliding, that it should not slide inwards or outward, that it will fail if it slide, right? So it should be safe against sliding. If it's unsafe against sliding, then we have to provide a shear key. So then we have to design a shear key. Next is design of toe slab. Then a heel slab will be there and the vertical stem will be there, right? So let's start. In this part, we are going to find out all the stability, all the initial sizes, all the earth pressure coefficients, check against overturning, check against soil pressure, and the stability of the against, and the design of shear key. In the next part, we will going to design the toe slab, heel slab, and the vertical stem, right? So let's start. What is the problem is there? Similar kind of problem was there. Then according to that, we have to put our data, right? The cantilever retaining wall is required to retain a earth 3.8 meter high above the ground level. This is the ground level, and this height is given, that is 3.8 meter. So we have to put 3.8 meter here. Then the inclined angle of the backfill soil. Inclined angle of the backfill soil is there. This is the inclined angle, that is delta. Delta is given is 15 degree. Okay. What is the unit weight of the soil? This is the backfill is the soil. The unit weight is given is 18 kilonewton per meter cube. Okay. What is the internal angle of friction? Internal angle of friction between the concrete and the soil is 30 degree. And the soil bearing capacity is given is 150 kilonewton per meter square. You have to put your data. And what is the coefficient of friction? This is the concrete and there is the soil, and if it try to slide, then there is a friction comes into picture, right? So coefficient of friction is given, that is 0.5, and FCK we have to use, FCK is M20 and Fy is 415, right? So now we have put all our data. Then the depth of a foundation is given by this formula. The formula is automatically put in this cell, and finally this 0.93 meter has been come out, right? But we have to take the larger size. So if I am adopting 1.2 meter, then the overall height comes out to be 5 meter, right? Next is width of the footing. That should be, these are the thumb rules. You have to follow all the thumb rules formulas by which you can design this, right? So formulas are override there, right? So if for the footing, that is the width of the overall base slab, it should be between 0.5 h. If we have find the overall height, 0.5 h to 0.7 h, right? So how much we can take? If you are taking 3, we have to take between these two. You can take anything from between 2.5 to 3.5, right? So I'm taking 3 meter, so 3000 mm, right? Width of the heel 0.5 of B, that comes out 1.5 meter. Thickness of the slab is h by 2, 417 mm thickness of the slab. So we are going to take, in the design you can take according to your choice, but in safe manner, right? So it is 420 is the thickness of the this base slab. So thickness of the stem at the top of the base slab is 210, so we are going to take is 200. So height of the stem, this is the height of the stem, comes out to be total height. This is 5000 minus this thickness, it comes out to be 4580. So we have put all the data. Now it has been calculated, all the forces, all the movements has been calculated. Like I'm giving you example how this calculated. This is W1, this is the base slab, and this is W1. It comes on a particular CG of this particular structure. So CG from the heel we have to take the distance. So W1, how we calculate the force? This is the area. Force is area into the unit weight, right? So area is, this is the length 420 into unit weight of concrete is 25 Newton per meter cube, and distance from the heel, you have to take the distance always from the heel. This is 1.5 meter. 1.5 this total 3 meter by 2, 1.5 meter. So the movement is force into perpendicular distance. So we have calculated the force and the movement, right? Accordingly W2 is there, you have to find the W2. So how you will find the force? Force is this area you have to find, and the concrete 25. So formula is there, area, this is 200 by this overall length 4580 into unit weight of the concrete, right? And how much the distance? Distance is 1.5, and 200 by 2, 1.6. 1.6 is there, right? So all these are there. W3 you can find, W4 you can find, that is for the backfill soil, and backfill soil you have to take the unit weight of soil, right? So finally it has been calculated that overall load is calculated, overall movement is calculated. Okay, height of the inclined portion is calculated. This is the, we have calculated, this is 1500, but you have to find this portion. How you will calculate? You have angle is there, so perpendicular on base is 10 delta, right? So it has been calculated 10 delta. So this height is calculated as 402. Okay, then earth pressure coefficient, the Ka coefficient, this is the formula for the coefficient. K is calculated as 0.373, Kp is calculated by this formula, right? Passive earth pressure coefficient. Okay, now the next step is force due to active earth pressure. Active earth pressure will be this, like Pa, right? So how we calculate the force? You have to calculate this whole height. It has been calculated, that is h plus height of inclined portion. You have already calculated 402. So finally the whole height has been calculated. Pa formula is Ka, gamma s is the unit weight of the soil, h dash, this is the h dash square by 2, so 97.95. but horizontal component you have to take, because this is in inclined portion, so you have to calculate the horizontal component, and vertical component, right? Check against the stability against overturning. This is the formula for overturning: 0.9 into stabilizing moment mr over overturning moment mo should be greater than 1.4. Okay, so overturning moment is, the formula is there, pa cos delta, that is the horizontal component, into h dash by 3. This is h dash, overall height, and it will generate on particular h by 3 from the base, right? So the overall overturning moment has been calculated, overturning moment, right? So the distance of resultant vertical force from the heel, you have to calculate this distance. Resultant vertical force is, we have calculated all the resultant vertical force. So where it will act a distance of x, right? Now how we can calculate x? Summation of m, total overall movement, divided by summation of w. It will be calculated 1.03 meter from the heel, right? So stabilizing moment above the toe, what is the stabilizing moment? So this distance multiply the overall load gives the stabilizing moment, right? So overturning moment in this direction, if it is in anti-clockwise, the stabilizing moment in clockwise direction. So you have to take the stabilizing moment should always be greater than the overturning moment, then it will be safe. So in our case it is 2.04, it is greater than 1.4, so hence it is safe against overturning. It has been already calculated, right? Now next is the soil pressure. Second thing, I have told you that the soil pressure of overall load on the soil should be less than the soil bearing capacity, right? It should be satisfied. So in our case, the eccentricity, the formula is there, eccentricity is calculated, it should be less than b by 6, so this is okay. So q max is the maximum pressure comes from the overall structure, right? So it is 117, we have soil bearing capacity of 115 given in the question, so it is safe, right? And by this formula 1 minus 6 e by b, the minimum pressure, because pressure is very important to calculate the moment by which we can calculate the reinforcement in toe, heel and vertical stem, right? So q minimum has been calculated 13.41 kilonewton per meter square. Next step is the check for stability against sliding. So next is the sliding. It should not slide. If it slide, then it can fail in inward or outward direction, right? So this is the formula: resisting force upon sliding force, that is the horizontal component, pa cos delta, should be greater than 1.4. In our case, resisting force, the formula is mu into summation of all the load. So it has been calculated. Mu is 0.05 into summation of all the forces gives you the resisting force, and the sliding force is the pa cos delta, right? So in our case, this formula comes out to be 0.93, which is less than 1.4, hence it is unsafe. So you have to provide a shear key, right? We have to design a shear key bottom at the base level. So what the role of the shear key? Shear key is provided as a cubical type of portion below the base slab, which will resist it to slide inward or outward direction. So we choose the dimension of shear key as 300 by 400 mm. So it should be noticed that the distance shear key should comes under the stem, right? It should be greater than this toe slab. It should not be outside this stem, right? It should be noticed. So if we choose 300 by 400 mm, you can choose 200 by 400 mm also, right? So we are choosing 300 by 400 mm. So D is 1100 mm. It should be noted that some assumptions are there to design a shear key. The effect of shear key is to develop the passive resistance over a depth h2. The shear key, what shear key do? Shear key provides a passive resistance inside, inwards, right? So we have a resisting force plus passive resistance, then it will resist a sliding force outside, right? So this is the main aim, to provide a shear key. Second is for computing the passive pressure below the toe. The top overburden of 300 mm is usually neglected. So this is the ground level. So this is the soil portion in front of the stem into toe portion, above the toe portion. So it should be noticed that above the toe portion 300 mm of soil is neglected to calculate the passive pressure, right? These two notes are there, right? So we have to calculate the h1 is calculated. How h1 will be calculated? This is already been calculated as 1200 mm, the depth of the footing, minus 300 mm, it is 0.9. B is, you have to calculate the B, what is B? This distance is 1100 mm, 10 delta, 10 phi. This is 0.64. Now we are calculating passive earth pressure, so PP. So this is the formula, Kp into gamma S to H1 plus A plus B. This is H1 plus A plus B. So this is the height for the passive earth pressure, right? So H1A plus B. So whole square by 2, this is formula, minus Kp gamma S H1 square by 2. This has already been taken, so we are subtracting this thing. So finally PP has come 69.05. Now we put the force already calculated. This is the force, resisting force, plus the passive earth pressure given by this shear key. Now if we put these in this formula, this comes up to be 1.59, that is greater than 1.4, hence now it is safe against sliding. So we have designed shear key by which it is safe against sliding, right? So these three steps we have done for stabilizing soil pressure, check against sliding, check against overturning. We have calculated the coefficient, right? So it has been calculated. In the next video, in the next part, we will design for the toe slab. We have to design the toe slab, then we will design for the heel slab, right? Then we'll design for the vertical slab. I will explain everything, each and everything. You have to put your data in only the pink cells only, right? So friends, if you like this video, please subscribe this channel for more design videos, and all the sheets are available on demand. Thanks for watching.